Welcome back to our YouTube channel. In this video, we are going to discuss about the next greater element, where initially for an element x in the array, the first greater element is the element that is to the right of the x in the same array. Let me pick an example. In this case, the next greater element for 2 is the element that is greater than 2 and it should present to the right side of it. Okay, and we're going to scan from here. 1 is still lesser than 2. Again 1 is still lesser than 2. We get 5, which is immediate element which is greater than 2. Therefore for 2, 5 will be our next greater element. And again for 1, we're not going to see anything. We're going to start iterating from here. At here we can see that it is still not greater, it is equal. Move forward. 5, again for 1, 5 will be our next greater element. And we are initially given with two arrays nums1 and nums2, where nums1 is the subset of nums2, which states that every element present in the nums1 is also present in nums2. And for every index I, starting from 0 to the length of the nums1, we have to figure out an index j in nums2 such that the nums1 of I is equal to nums2 of j, which states that if I have an array 4, 1, 2 and another array 1, 2, 4, I'm gonna figure out here the index is 0, here it will be 2. I have to figure out the same element present in nums2, which like for 4 here it will be the element, for 1 here it is, for 2 here it is. And this is the thing that is been said in the first line, and we have to determine the next greater element of nums2 of j in nums2. As I said earlier, we have to figure out the next greater element for every element, but in the second array, not in the first array. Got it? And we have to return the answers of length size of nums1 if there is a next greater element, or else we're gonna make sure I have to return -1. In order to better understand the problem description, let's see the example 1. Here the first element is 4 and 4 is present at the index of 2 in the nums of 2, and we have to figure out the next greater element for 4. And to do that, we are going to start iterating from the next index, which is 3. 3 is the element present at the index 3 is 2, which is lesser than the element 4. Therefore there is no element, and we're going to move forward. And when we move forward, we're going to see that there is no element present. It's end of the array. And for 4, there is no greater element. We're going to store minus for 1 it. And coming to 1, we're going to pick where 1 is in the nums2. Here it is. And going to start iterating from the next possible index. We're going to see that next index is 1, which is have the element as 3. Since 3 is greater than the element 1, therefore 3 is the next greater element. I'm gonna store it. Move it forward. Where does 2 present? 2 present at the last index. We're gonna move it forward. Therefore, we're gonna see that there is no element present. Therefore, again I'm gonna make sure -1. -1 signifies that there is no greater element. Next greater element. Sorry, there is no next greater element. And let's quickly look at another example. 2. Where does 2 present? Here. What is the next greater element? Start iterating from the next index. Yeah, I got 3. 3 is greater than 2. Therefore, the next greater element is 3. 4. 4 is present at here. I'm going to start iterating from the next index, but it gives me out of array. Therefore, it doesn't have anything. And this is the array. And you're going to see that it is the same output as expected. And let's quickly discuss the brute force approach for this solution. As I see that we're going to start at 2, and we have to figure out the index where is present in the does 2 present in the nums2. 2 is present at the index of 1. Okay, therefore I'm going to start iterating from the next possible index. Therefore I'm going to start iterating from 2 to nums2 dot length. Got it? Again, yeah, I'm gonna start iterating from here. 3. Does 3 greater than 2? Yeah, it does. Therefore, I should append 3 to the answer array. We are done with this. Again, as quickly as we found a greater element, we're gonna break the and move it forward. 4, where does 4 present? Here at the last. We're gonna start iterating from the next index. The index for this will be 0, 1, 2, 3. 3 plus 1, which is 4. 4 to nums2.length. But here we're gonna say that we can 4 does not present in the nums2 because its length is 4. We're gonna have elements up to length minus 1, which is 3. But I'm gonna looking for 4. It is not possible, therefore minus 1 will be my answer. Append it to the answer array. And this is the same thing that we are seeing. And let's quickly code this up. The brute force approach for this is to start from the next index where the element is present. For 2, the element is present here, we're going to start iterating from the next possible index. And let's quickly code it up. Initially, we have to figure out where does this current element present in nums2. I need the index. For 2, its index is 1. For 4, its index is something 3. 0, 1, 2, whatever. Therefore, I require this. Therefore, in order to do that, I'm going to start iterating from 0. I'm going to start from 0 to nums2.length, and we're going to store that hash map. It stores a key value pair. We're going to initialize the empty hash map where it stores the element and its value is the index itself. For 1, I'm going to store 0. For 2, I'm going to store 1. For 3, I'm going to store 2. And for 4, I'm going to store it as 3. This is the same thing that is present in my hash map. Got it? And the next thing is to iterate from the next possible index for every element in nums2. Like for I, which starts from 0 to nums1.length, I'm going to start trying from the next index. Let's say the start variable, which is the hash map of nums1 of I plus 1. We're going to start iterating from the next possible index, right? Therefore, we're going to check that if start is equal to nums2.length, if it is so, we can say that we're going to do nothing but append a minus 1. Answer is an array that we're going to return at the end, append minus 1 and break here. But what if the start is not equal to nums2.length? Then if it's so, we're going to start iterating from the next index. Got it? For j, starts from the start plus 1 goes until nums2.length. And if in case, if I found that if nums2 of j is greater than nums1 of I, then again I'm gonna answer that append nums2 of j and break here. But if I see a example like 2, 1, 1, and again see that there doesn't consist of any duplicate numbers in nums1 as well as nums2. It is clearly given in the constants, all are unique. Therefore I'm gonna check something like 2, 3, 4. Sorry, I have to write this in decreasing order. 5, 4, 3. Got it? I'm gonna start iterating from 4 for 5 and gonna check that there is no greater element for 5. And at this case I'm gonna end the for loop, right? The for loop will be ended and I'm gonna come at here. So I'm gonna come at here, this signifies me that there is no element. Again, I should append minus 1 because if there is a good pair that is available, I'm gonna break it here itself, and remaining statements will not gonna execute it. In the same way, if I break it here, this statement will be not executed. This I come to this statement only if I not found a greater element. That's the only case. Or you can say that we can still erase this entire case. Yeah, got it. And just as simple as it is. Got it? And the time complexity for this approach is order of m cross n, where m is the length of nums1, n is the length of nums2. Space complexity is order of n for hash map, and another order of m, order of n for hash map, and order of m for returning the result. But it is mandatory to return the array itself, therefore we not consider this is the space complexity that we have been using in this algorithm. And let's quickly discuss the optimal approach for this problem. The problem with our previous approach is time complexity is order of m cross n, and we're gonna move it towards a good time complexity like order of m plus order of n. And our optimal solution uses is the same time complexity, but it uses a data structure called stack. Why? Because we have to store what's the next greater element for every element present in nums2. For nums2, I'm gonna start iterating from the end. Here there will be no element towards the right of 2, so its next greater element is nothing, -1. For 4, again I'm gonna see that there is no greater element, therefore again it's -1. For 3, the next greater element is 4, therefore 4 will be the next greater element. For 1, it is of course 3, and we are done with this, right? Therefore I'm gonna see 4. As we have been said earlier, nums1 elements are all present in nums2. Got it? Therefore for 4, what is the next greater element? -1. Got it? Done. For 1, what is the next greater element? It is 3. Okay. For 2, what is the next greater element? Again nothing, -1. And see the beauty of this, the same. And here we're gonna take a time complexity of order of n for traversing from the end to the beginning. Again from here to here it takes a time complexity of order of m, which will result in order of m plus order of n, because we do this thing first, which gives me order of n, plus we do this thing which gives me order of n. And let's quickly write a pseudocode for this approach. Okay, we are going to start iterating from the last index in the nums2. Therefore for I which moves from nums2 dot length -1 and goes till 0. Got it? And initialize the stack to empty. If there is a stack, got it? If there is a stack, and stack dot top, which gives me as the stack of -1, if it is lesser than the current element, which is nums2 of I, got it? If it is lesser than the nums2 of I, then I gonna pop. But how many times do I do this operation, like popping out? Until and unless the stack of -1 either is greater than the nums2 of I, or else there is no stack, because I got checking, right? Until it holds the two conditions, the stack should be there and stack of top should be a greater element, therefore I gonna state as it is. But whenever I found a stack of top which is lesser than the current nums2 of I gonna keep on popping, therefore I gonna replace this with a while. Got it? And you're gonna check that if there is a stack, if there is stack, means there is something element present in the stack, therefore we're gonna store next greater element of the nums2 of I, the stack dot top itself. Or else if there is no stack, means the stack is empty, therefore the next greater element in this case will be nothing, -1. Got it? and it is as simple as it is. And let's quickly simulate this approach. We're gonna add 2, and at the end I'm gonna push into the stack what is currently, like currently element is nums2 of I, got it? Therefore we're gonna push it in the stack dot append nums2 of I, got it? And let's quickly simulate this approach. We are at 2. You're gonna see that there is no stack, got it? This statement will be not executed, this also not executed, and I comes to else block, and I'm gonna make sure that NGE means it is a dictionary which stores key and value pairs. Here the key will be the element itself and the value is the next greater element, and NGE of 2 will be -1, got it? We are gonna move backward. But before moving to backward, the stack will be pushing an element called 2. Again we get a new element 4. There is a stack and stacked up top which is 2, got it? It is lesser than the current element which is 4. Therefore we're gonna pop. Is there a stack? No. Else block is executed, and next greater element is of 4 will be again -1. Stack that upon the current element which is 4, got it? Again move it forward. We're gonna present at 3, and while stack, yeah, this stack is there, but stack dot top which is 4 lesser than 3. No, this statement is false. We not enter into the while loop. Yeah, there is the stack does contain some elements. What is the top dot stack? 4. We gonna assign NG of 3 is stack dot top which is 4, got it? Move it further, but before moving gonna go append 3 to the stack, and the current element is 1, while stack and stack of -1. Now the new top will be 3 lesser than 1, false. Again while loop will be not executed. Coming to the next statement, if stack, yes, there is a stack, therefore the NGE of 1 will be the top dot stack which is 3. Now this will help us a lot, which states that for every element what is the next greater element. For 2, -1. For 4, -1. Like for every element present in the nums2 we're gonna get the its next greater element, and based upon this we're gonna make our answer. And taking the help of this, again I'm gonna iterate from the starting for I in 0 to nums1 dot length. As I said earlier, every element is present in nums2, therefore there is no need to check that whether this element is present or not. I directly gonna use the value. And answer will be the returning array ans dot append NGE of current element which is nums1 of I, and again at the end I'm gonna return the answer itself. And let's quickly simulate this. For 4, what is the NGE of 4? It is -1. Yeah, -1. For 1, what is the NGE? It is 3. For 2, what is the NGE? It's -1. And this will be the resulting array. And let's quickly discuss the time and space complexity for this approach. The time it takes is, this loop takes a time complexity of order of n, which is n stands for nums2 dot length. Again, yeah, you can see that this while loop takes a time complexity of something else, right? Order of like order of n or order of m, but it doesn't. The entire for loop along with the while loop takes a time complexity of order of n itself, and this takes a time complexity of order of n. Entire term complexity is order of n plus order of n. The space complexity we used is again order of n for a hash map, and this will be the optimal solution for this problem. And if you like understand everything, then please do like and share.